in terms of the exam, it's not meant to be tricky at all. So as long as you're comfortable with the homework questions, the main concepts that I'll go over, you should be completely fine. And the time, as Professor said, it's 2 hours, but it's really not designed for 2 hours. So hour and 15 minutes at most, I'd say. You should be able to get it finished. In terms of the topics, everything is covered, including the wheels lecture. And yeah, I'll give a few minutes to other people, and then 11:10 I'll start sort of going over my notes for sort of a review of what we've covered so far and what things are important. Yeah, if you have any questions till then, we can go over them.
Yeah, I have a question. So if the wheels homework is due next week, or like per se it's due, we won't have the answers for that homework. So how will we know we're on the right track for the test for that problem?
So yeah, so the rule with that homework is if you turn it in by next Tuesday or next Thursday, you will get the solutions in private message from TAs. So that way you can like check it. But if you're planning on just working on it and not necessarily turning it in this week, then you can ask questions on Piazza from me, Mike, Nikolai during office hours, and then hopefully we can help out with understanding those. But yeah, the only way you can get the solutions is by actually turning it in this week. So then for people that do turn it in this week, we'll just email them the solution.
Thank you.
Yep. Any other questions? Okay, I guess I'll just get started since it's 11:10. All right, so let me share my screen with you guys. All right. So all right, can everyone see my screen?
Yep.
All right. Okay, so all right, so this is review for exam 1. And then Aaron will do something like similar-ish, but I'll try to focus more on the important stuff rather than like everything. So started talking about manifolds. And we say that these manifolds are important because we use them to describe our configuration space for a robot system. So we said something like a torus would be a manifold because it's not self-intersecting. So something like this would not be a manifold because it's intersecting itself. And then in general, anything that locally looks like Rn. So like if I look at any local point on here, 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 it looks like Rn, then this is a manifold. So here are these sort of points. These are the problematic points that by definition, we call this a non-manifold. And so again, why manifold is important because we use it to describe our configuration space. So for a two-link planar arm, if we have Q1 and Q2 as our sort of states, then we can imagine Q1 would be if we go around this circle, and then Q2 would be for every slice of this donut. Q2 would be if we go around the slice. So basically by having this manifold, we can, any point in our configuration space can be geometrically described. Now, as we have more and more dimensions, we can't really visually see what's happening, but that's the idea. So if you have a 10-link pendulum, then we can't really say how it looks like, but that's the idea. Then we talked about tangent maps. We said if at any point on this manifold that represents a position, so I'll just draw the manifold again. We said at each point, if we draw a tangent plane, that would be a tangent map. And then if we do that for every point along the manifold, for all possible points, then we get a tangent bundle. So tangent bundle was collection of all of these tangent maps. And this is basically, this represents all possible velocities. So the tangent bundle basically describes all possible velocities. So our manifold describes all possible positions or our configuration space. The tangent bundle describes all possible velocities. And then later on realize that this basically looks like our Jacobian matrix. So we have our matrix of partial differentials. Xn, and then I won't write down all the. So then this is basically what we refer to as our tangent map. And then we said later on, it becomes important because it's basically our Jacobian. Can I go to the next page? Are we good? Yes, no? All right.
We're still
Oh,
copying.
sorry. Quick question.
Yep.
When we talk about like the collection of tangent maps, is that the same as an atlas?
So no, atlas was just your mapping. Collection of tangent maps is your tangent bundle. So atlas was look, if you can cover a manifold in n different ways and you cover all of those ways, the collection of all those would be your atlas, right? So if you have like say a 2D plane, Aaron talked about this example where you could cover it say like this or like this, right? So this is one map. Another map could be if you cover the two quadrants here and here and then do the two quadrants like this, right? So then there are a bunch of other collections that would satisfy this covering. And then so if you collect all of them, that will be your atlas or a collection of all the mappings. Your tangent bundle is a collection of tangent maps, right? So if I have my derivative at each point in this configuration space, then that would give me a tangent map. And if I do that for every point on that configuration space, that'll be a tangent bundle.
Okay, cool. Thank you.
Yeah. So then we talked about rotations. Introduced the rotation matrix. And we said that it looks something like this. And the idea was that we can describe a rotation of any frame with a matrix of this form. So if I have a frame A and I have a frame B, and they're misaligned by theta, then I can describe A relative to B as a rotation matrix, right? So that would be a rotation matrix. Okay. Then we started talking about velocity. So we had two types of velocities. We had our spatial velocity. I'll just write the hat version. Then we have our body velocity. And let's briefly write the equations for these. And so it's really important for you guys to know how to go from one to another. So how to write a spatial velocity from a frame with respect to another frame, how to write the body velocity, and then we use the G, which is our rigid body transformation matrix. So this is our rigid body transformation. And that was basically our R matrix. So we had our R matrix here, and we had some P hat here, and then the bottom rows were just 0, 0, 0, 1 in 3D. And so here we had our X and Y, right? So that's in 2D or 3D. In general, it doesn't matter which one you do for the exam. Most of I think all the questions are in 2D. So, but in generic term, you can always write things in 3D and it should still be fine. So this was our G that describes not just our rotation, but also our translation. So if we had a point here and a point there, and we had a frame S attached here, and another frame, say A attached here, then this matrix, the translation part would correlate to this vector. So this would be our P hat. So by what X we're over, by what Y. And then this orientation difference, theta, would be captured by our rotation matrix.
And the P vector is always expressed in coordinates of S, right?
Correct. Yes, from the source coordinate. So if S is your source and A is your destination, your P is always expressed in the source. So far, the important things we talked about: manifold, tangent maps, which is basically a matrix of partial differentials. We talked about rotation matrix, rigid body transformation matrix, spatial velocity, body velocity, being able to get them in different situations. And then the next important thing was how to go from body velocity to spatial velocity, or the opposite. So understanding this conversion that involved the adjoint matrix, right? I'm not going to write in detail like what these are. These are all in notes. You can just like copy it down, but just understanding the important stuff. So basically this adjoint is a mapping that maps your spatial velocity to body velocity. So if you had a question where you were given spatial velocity or body velocity from one frame to another, and you were asked to translate it to body or spatial, your adjoint of your rigid body transformation inverse would be the mapping you need, right? And you can have all this down in your like equation sheet. Okay.
A quick question.
Yep.
In the previous one, what's the difference between P hat and X and Y? I thought those were I thought P hat was
So that's,
X and Y.
yeah, that is the X and Y. Sorry, that is the X. I just wanted to, because P hat, people say, oh, what is P? This is just your X and Y. Yeah.
And a
You
one
have the
down there, right?
Yes, one down. Or one down here. Let me just, yeah. So like the equations, you all have them in the notes. I just want to sort of focus on what's important and what you really need to know for your preparation. Because obviously there's a lot of stuff covered, but just want to sort of make sure that you guys know like the key things. So, and then the last key thing was here, knowing how to go from spatial to body through the adjoint mapping, and the opposite. So if you have spatial, how do you go to body? If you have body, how do you go to spatial? Okay. Then we talked about forward kinematics and inverse kinematics. And this is extremely important. So your forward kinematics is a mapping from your configuration space to your workspace, and your inverse kinematics, as the name implies. So this is basically our GST, rigid body transformation matrix. And the inverse kinematics is the inverse of this mapping. So we go from workspace to configuration space. And this would be our GST inverse, right? So for example, if you have a 2-link arm again, right? And you have your spatial frame and then your tool frame that's attached to the robot's end effector. Then you can always, as we described in the previous slide, you can always write down your rigid body transformation matrix. This is your FK map, or your forward kinematics map, that basically says if my robot is at a configuration Q1 and Q2, where is my end effector, T? The inverse mapping says if I want my end effector to be at T, where should my Q1 and Q2 go? Right? So these are very important. Obviously in the exam, you don't have access to MATLAB. So like, there's not gonna be like a computational inverse kinematics where you have to do an optimization, but understanding that, oh, you have to minimize, you have a G star that corresponds to the optimal configuration that takes your tool frame to your desired point. And then you want to minimize that difference. So you want to find a Q1 and Q2 set that minimizes this, let's call this T star, that minimizes this T star to this T. So understanding it sort of conceptually would be sufficient. You're not going to be asked to do like any crazy computation. Okay, so forward kinematics, inverse kinematics, and then we talked about Jacobians and body velocities in the context of manipulators. So again, I stressed this before, but this is also a very important equation to just know, is that the Jacobian is a mapping between your configuration velocity to your spatial or body velocity, depending on what the Jacobian is. So for spatial velocity, you have the spatial Jacobian. For body velocity, you have the body Jacobian, right? And at the end, all the Jacobian is just mapping of velocities. How can you map how fast your joints are moving to how fast your end effector is moving? And so that is a very, very important equation to understand. Okay, equivalent to Jacobians, we talked about forces and torques and how Jacobian transpose comes in. So we said Jacobian maps configuration velocity to body and spatial velocity of the end effector or whatever body we're referring to. And then we said that torque would be so then our Jacobian transpose is a mapping of forces to torques. So then we had this homework problem where we talked about if we have our manipulator and we have some mass here, what torque do we need to apply at joints Q1 and Q2 to counteract this mass M, right? And so what was important for that is to understand that our Jacobian transpose maps this force at the tool frame. So this M, for example, let's say F equals mg here. So this force, how does it map to the torque in Q1 and Q2, right? So just like how we can map velocities from configuration to body end effector, we can also map torques and forces, right? So these two equations, I can't stress them enough, they're very important. And then the same version you can do with spatial Jacobian. I just didn't write it. Okay. And then we talked about, so this force here actually, it's a wrench. So we said that this force that we refer to, or we say a wrench, in 3D is a 6x1 vector, right? So you have your fx, fy, fz, and you have your tau. And this is in R6. So like every single one of these have 3 components. So that would be fx, fy, fz, tau x, tau y, and tau z. So when we refer to mapping wrenches, just know that it's not just forces, it's forces and torques. And then if it's in 2D, you can always just consider those appropriate dimensions. right. Any questions so far?
If we had a force rather than a torque actuator, would we still just be able to use JVST?
If you had a force rather than a torque actuator, yes. Yes. So yeah, in that case, yeah, you always can. So all this Jacobian does is just like, okay, if I have some force, so imagine you have an arm that's pushing on an object, right? You want to know if you are applying a force, what does the object feel, right, at its coordinate? Or if the object is pushing on the robot, what the base feels, right? So all these sort of transformations moving from one frame to another, the Jacobian takes care of the mapping. Jacobian transpose for force. So yeah, so you can imagine if you have like just one fun example, if you have like a legged robot and you want to have a specific force applied to the leg and you're planning for that force, then you can solve what torque your actuators need to apply to satisfy that force. For example, if you want to keep the robot stable, things like that. So this is sort of the motivation for it. Okay. And then, oh, one important thing, just like how we had the spatial and body mappings, we can have spatial and body forces mapping through the adjoint. Again, these are all in the lecture notes. I'm just sort of highlighting the important stuff here. So if you recall on 2 slides before this, we said that our adjoint inverse can map, so this was the equation. We said, all right, so we said our adjoint inverse can map our spatial velocity to our body velocity. All right, so we said this was the equation we had before. And we said that the adjoint inverse maps spatial velocity to body velocity. Now we're saying the adjoint transpose maps our spatial force to the body force, right? So again, 2 things I want you to take away from this. 1, understand how velocities change from reference frame to another. How can you transform spatial to body, body to spatial, and moving between coordinates? And then same thing with forces. So anything you do with velocities, you should be able to also do it with forces and torques. So make sure that you have a good understanding of these transformations and how they're applied. Okay, and then towards the end, which was your last homework, you guys talked about your grasp map that maps your contact forces to your object wrenches. So this grasp map, even though it was very complicated to calculate, you had your adjoint, you have your basis and all that. At the end of the day, all it is just a mapping, right? So I am pushing on an object with some force. I just want to know how the contact force I'm applying maps to the wrench of the object, right? So that's really all it is. And then you also had your hand Jacobian. So grasp map, you know how to calculate, it's in lecture notes. And then you had your hand Jacobian, which mapped your contact velocity. So I say JH, mapped your contact velocity to so I mapped your joint velocity, not contact.
Hey,
Mapped
Arlen,
your, yes,
can I ask you a question? Am I
Sure.
interrupting?
no.
So actually on the question about the body velocity up there. So,
Sure.
say if there's like a 2-finger robot that we had like in the homework, so would that change if like depending on like where we put the body frame on that robot? Like, is that
Yes,
so we
the
would have
body
to keep
velocity?
it- Yeah.
Yes, so the body velocity is assuming you have a frame. If you're sitting on that frame, what velocity do you feel? So depending on where you put that frame, that changes. So if you put it at the end of the link, for example, you get a different body velocity than if you put it in the middle of the link.
So when we were to be asked like get the body velocity, would the question like specify like where to put the frame, or do we just put it where we want and just calculate GAB and everything?
So, yeah, the question will be clear. Mostly they'll ask you, okay, this is the frame, write the body velocity in that term. But if they don't, you can define your own frame, and we're not gonna like mark that as wrong. If we don't specify, you can just attach a frame to center of mass or end of the link and write it with respect to that. So if we make a choice specifically, then you have to write it with respect to that choice. But if we don't, then you can just specify your own frame on the body, and yeah, that's fine.
And for the A-frame, we usually use that for the stationary frame, right?
That's generally at the base, yes.
Okay, yeah, thank you.
So that's it, sure. And then the reason why it's different, because if you look at up here, the reason why it's changing is because you have this rigid body transformation matrix. So depending on where you are along the link, your entries are changing, right? So if you have your frame attached to the end of the frame, your GAB is different than if you attach it to the center of mass, let's say, right? So that's why it's different where you look at with respect. We talked about, okay, so we said grass map was the mapping between contact forces and object wrenches. And like, once you know you need a grass map, all you do is just you follow the computation. What's my BC? What's my adjoint? What's my rigid body transformation? So you just step by step go through it. There's really, if you just stick to the procedure, you should be fine. And then your hand Jacobian was mapping your joint velocities to your contact velocities. Okay, and then we said that two important things that cause a lot of confusions was the null space. So we said that the null space of G gives us internal forces. And I'll explain what we mean by these. And the null space of JH would give you internal motions. Okay, so a lot of people ask, well, what is internal force? What is internal motion? So internal forces are the forces that do not disturb your equilibrium. So if I can apply a force to my object in a way that it doesn't disturb its equilibrium or it doesn't move it, roughly speaking, then that's an internal force. Now, what does it have to do with null space is what people ask. So a null space, basically, how do you get a null space? You say for G, for example, you say G times X equals 0, and you solve for X, and G is your Grassmann. So what does this mean? It means my vector X mapped through matrix G always maps to 0. So it means no matter what I do with my vector X, these set of X values mapped through my grass map will always map to 0. So intuitively, you can now see the connection, right? So it means those set of forces, contact forces, will always map to 0 force on the wrench, or 0 equivalent force on the wrench. So that's why we call them internal forces, because it means if you apply those forces, the wrench won't be affected, so the object won't move, right? So this is intuitively what it means and how it's connected to the null space. Same thing with the hand Jacobian. I think Aaron made a post about this on Piazza to clarify everything. But yeah, so same thing. Null space of hand Jacobian would give you your set of possible internal motions, and that's how you get the null space, by just multiplying your matrix of interest by your variable, which is X, in this case is force or joint velocity, and then equal to 0, you solve for the X's. Okay, almost there. And then last lecture, you guys talked about wheels. And this was, I think, the first time you talked about constraints, which is a big part of this class. And so the constraints for the wheel was one, the traction constraint, and that was that your r theta dot equals v. So if you call our velocity here v, and the wheel is rotating by theta dot, and r is its radius, assuming we have no slip. So meaning that we have perfect traction, the wheel doesn't spin by itself or doesn't free spin, this relationship needs to hold. So it's important to know that if we have sliding or slipping, then this no longer holds. This only holds if you have no slip assumption. And then you also had your, I won't write it out fully, but you also had your lateral constraint saying that, I'm just looking at it from the top view. If you have a wheel like this, you cannot have x dot or velocity in this direction. So so basically you can only move along its heading, right? And so I would say for wheels, what's important for you to know is, one, being able to write your constraints. And then two, verify that your constraints make sense. And what do we mean by that? Make physical sense. And that basically means that if you're writing out a relationship, show that, okay, it actually is true that I get, if this is my x and this is my y, this relationship means that I will have no velocity in x, right? So being able to make sense of what you're writing. So write your constraints, number one. And then two, once you have your constraints, make sure it makes sense, right? So if you're getting a constraint that means you have some x dot velocity, then that really doesn't make any sense, right? Okay, so that's sort of the stuff I wanted to cover. In terms of the exam, I think I talked about the general format. And this review was basically the stuff that I thought was very important to know. So understanding configuration space, tangent maps, spatial and body velocities, how to move between them, moving between frames, forward kinematics, inverse kinematics, Jacobian mapping velocities from your joint to your end effector, and Jacobian transpose, mapping your forces to your torques. Grasp map, hand Jacobian, the null space of each, what they mean. Oh, one thing I missed, singularities. If you write your Jacobian, when do you have singularities? When you lose rank. So yeah, really, there's really nothing else that's in there. So now I can take any questions, and if there's any sort of confusions, we can go over that.
Ardalan?
What's up?
Could you really quickly explain again internal motions?
Yes. So internal motions come from your null space of your hand Jacobian, correct?
Yeah.
Okay. So first of all, what do we mean by null space? And null space, when you solve it, you say, let's say my hand Jacobian is GH, and then I'm solving for theta dots. So this is how you get your null space, right? So you set it equal to 0 and you solve for theta dot, right? So this basically means find me the theta dots that if I map them through my hand Jacobian, it will give me 0 resulting velocity at the contact, right? Or in other words, if I have my two link, now let's say it's symmetric, we have the same setup on the other side, and I have my contact frames, these velocities won't actually cause any motion of my contact frame, right? So that's basically what we mean by internal motion. So it means I can move my finger, but that movement won't cause any movement at the contact, right? And obviously there are a lot of assumptions here. So we assume perfect friction. We assume that we always remain in contact, so we don't like lift off. We don't slip. So all of these are assumptions we're making, but conceptually, this is what it means.
You have no movement of the contact frame.
Yes.
Okay.
Causes no motion, and that helps by understanding the mapping. So hand Jacobian maps your joint velocity to your contact velocity. And the way we define contact velocity is we assume that the two bodies are in touch, and then we define a frame at the contact point. And so that's what we mean by contact velocity.
Okay. Okay.
Yeah.
Thank
And so obviously you can have like ugly things like, oh, I'm slipping, or like I have a rough surface. Like we just assume a perfect scenario when we have perfect friction, objects perfectly in touch, and we just assume that's the case for our definition.
Okay. Thanks.
Yep.
For the exam, should we be familiar with, actually, no, it's a silly question, sorry.
So for the last homework, I did like null of my hand Jacobian. It was empty. Does that mean I screw up my hand Jacobian probably?
So, okay, this is one thing. Just because you're null, the null space doesn't exist because you're doing it in symbolic form. But there are configurations that make you lose rank. So you have to find those. So let me actually be clear here, because I know that's a common problem. So if I have a full rank matrix, I'm doing some linear algebra here, my null space is 0 or is empty. Does anyone know? Are we clear on this? Okay. As soon as my matrix loses rank, the sum of my matrix rank plus my null space needs to be Rn, or needs to be n, sorry, if n is the original dimension of the matrix. So let me do an example here. If I have a 4x4 matrix that's rank 4, then my null space is empty, right? Because I can linearly, independently cover all the dimensions. But if I have all of a sudden a rank deficient matrix 4x4, so if now my rank is 3, now the null space is 1. If I have a rank of 2, now my null space would be 2. So the dimension, the rank plus the dimension of your null space should match your matrix dimension, always, right? So if you solve it symbolically, sure, you might find a case where there's no, like it's just full rank, right? But in the hand Jacobian example, and we'll post the solutions after everyone turned in the homework, but in the hand Jacobian case, at specific configurations, you will lose rank. So don't just look at the symbolic form. Think about like, okay, what happens at singularities? Will it lose rank there? And then if yes, then that means you have a null space there. So make sure that you cover the edge cases. So sure, your symbolic matrix might not lose rank, but if you plug in singularities, let's say theta of 0 or theta of 90 degrees, or sorry, 180, then you might actually get a case where it does lose rank. Did I answer your question?
Yeah. And then to be clear, losing rank could be losing a column or a row, right?
I can't hear you.
Sorry. Losing a rank is you can lose a column or a row, or is it only? Yes, basically. Yeah. So it means that, so if in this case, if I'm full rank, it means I have 4 linearly independent equations, right? From my 4x4 matrix. Now, if I have a rank 3, it means I only have 3. So 1 would be sort of coupled.
Well, hold on, because your hand Jacobian isn't square, right? So I think it's just the column space that you need to worry about.
Yes, correct. Yeah.
The convention is that if it's non-square, you have to select with whether it's columns or rows, and because it's always more columns, I'm pretty sure that's why it's usually that case.
Yeah, that's true. So if it's not square, then. But it's just a generic case. I'm just assuming it's a square matrix to communicate the idea. Yeah, because people say, oh, why my null space? What does it have to do with internal motion? So that's sort of what I'm trying to get at with it.
And generally, should we also be looking for internal forces at kinematic singularities, or is that only likely to give us internal motions?
It's so generally speaking, singularities do give you internal motions, but I wouldn't
I wouldn't check intuition for that. In those cases, I would just run through math and see what it says, because a lot of these cases, it gets tricky. And it's really hard to have a visualization of what's happening. So I would just recommend following the math, even though that's generally a correct assumption for internal motions. But I would say just check the math and trust the math in this case, because yeah, that depends on your configuration, depends on the specific scenario you're looking at. So yeah.
Thanks.
Is there?
Sorry.
I guess
Go ahead.
I'll just follow up to what I was saying. Is there a better way to do the math than to just look for kinematic singularities and plug in those values, or do you actually want to solve the matrix for linearly dependent columns?
So I would
Because
say for the
like
purpose,
in the last homework, I think, you know, there are 4 values that we have to look for, and I think it was, I realized what I should be looking for because I thought about the kinematic singularity in the last homework. But if I hadn't, is there a better way to figure out what those instantaneous internal motions would be?
so a better way would be if you have MATLAB and you just like plug and chug. But for the purpose of the exam and for the scope of the class, I would say just looking at singularities is fine. Yeah, those are the interesting points for us. And I don't think we're gonna like ask, oh, find all of these scenarios. Like, as long as you can run through math and show that you understand what these concepts mean, like that's where the test is. So yeah, there's not gonna be any tricky situations where you have to really find this configuration that would make it rank deficient. So don't worry about it. Rachel, do you have a question?
Yeah, so just kind of to summarize everything we've been saying, I'm gonna propose something and you tell me if this is correct. We are given a problem in which we want to find internal motions. We start by finding our hand Jacobian. From our hand Jacobian, potentially we, find the determinant, or like when the determinant of that hand Jacobian is equal to 0, for example, we know that there would be a singularity. Therefore, we know that at that particular configuration, there will be a certain potentially set of, quote, internal motions that are determined by our like Q dot matrix, such that nothing is going to be moving. And then we report all of those internal motions with respect to the relevant configurations.
Yeah, so when you solve for theta dot, it gives you a set of, so you will get a matrix like, say, like this, right? Let's say. But this means like any multiply of these ones would work. So you get a set of velocities. So like if this is like 0, 10, 0, 10, this would still satisfy, right? So,
right.
So this would give you not just one velocity, it gives you a set of velocities that would work. So that's something to be like aware of.
Okay, that makes sense. Should we write something in that case where it's like, for example, at Q1 is equal to 0, let's say, we have that 0, 1, 0, 1 matrix times K, and K can be any real number.
Yeah, you can just say that this is how our null space looks like, and so any multiply of, yeah, because all we care about is the space, right? If you find the space correctly, then it's just anything that expands on that space still counts. So also, you said determinant. Matrix isn't square, so
so
you can do like column rank.
Now this last homework where we kind of had like an upper kind of square matrix and a lower kind of I was able to get my columns to cancel when I considered particular columns canceling each other out. And I did that by saying, oh, okay, if I take like this times this and minus that times that and set those equal to 0, I was able to like mathematically determine which configurations would be the ones where I would run into that issue instead of just kind of guessing random angles until it made sense.
Yeah, I mean, in general, interesting things happen around around singularities. So definitely I would say check singularities in these cases. Whether you're trying to find, for forward kinematics, you're trying to find singularity, that's obvious. But even in these cases, generally with ARM type questions, anything is normal until you're close to a singularity. So that's always a good thing to check regardless. And I don't think we'll get any trickier than that for the exam. So
JH is a block diagonal matrix, right? So for each block, you can actually check internally if there's linear dependence between the columns, and that'll give you,
sure.
You can do it that way. I think that's what you were saying you did, Rachel, and that should work.
Yeah. Thank you for that much more eloquent explanation.
Yeah, so yeah, in general, yeah. Just make sure you check singularities. And yeah, again, the focus isn't like to give you some tricky question and see who can do the trick question better. It's really to cover the important bases. So pretty much the things that I went over. If you know those, you should be fine.
Oh, thank you.
Yep. Any other questions? I just stop sharing so it's not.
Multiplicative inverses and commutations. So the inverse of the adjoint is the same as the adjoint of the inverse, right?
Correct.
And then G can be inverted, R can be inverted. Can P hat be inverted to get if you have a P hat AB, can you invert that to get P hat BA?
Generally P hat is trivial to write. I don't think you need to do
okay, yeah.
P hat is just translate, like, yeah, you can just
it's also a 3-row 1-column matrice.
Oh, sorry, no, I'm thinking of
yeah,
P,
so you want
V.
negative of it, right?
Yeah, so negative multiplying P by negative gives you the P the other way.
Yeah. I mean, in general, I'd say for like translation vectors, just doing it like visually is a lot easier. Especially that I don't think we'll give any crazy like 3D complicated thing. So yeah, just do visually for that, and then everything else should be invertible. So like these little tricks help a lot. So knowing that, oh, GAB is the inverse of GBA, you know, a lot of times you're like, oh, I have this, but I don't have that. So you can just, you know, use these little tricks, and it helps a lot. Right, good questions. I guess, is everyone now clear on internal forces and internal motions? Okay, good.
So just going back to that, so essentially just finding the null space at one configuration isn't enough. We should try to find some singularity for which we can get a null space and just keep searching until we can get that.
Yeah, and again, the question will be specific, and it's not meant to be tricky. So yeah, I would say definitely always check singularities, because, you know, those are the interesting points in general. And yeah, that should be okay. So it's not like, oh, you have to search for this 58.5 degree angle that makes it. Yeah, okay. It's not like that. Yeah.
Okay, thanks.
Yeah.
If we have multiple wrenches applied on a body, and we want to use the torque is equal to the Jacobian inverse times the wrench, do we just sum all the wrenches at a point?
If it's all at one point, yes. If it's at different points, you have to move them all with respect to one point and then some. So like if you have multiple wrenches, one is applied here and one is here, you can't just add them up. You have to bring them both to one point and then add that up. So yes, you can add the resulting wrenches that way, given that they are with respect to the same frame. And that's a very good question and very important. Because in a lot of times,
we just do that with the adjoint inverse transpose, right?
Yeah, yeah. Because in a lot of times, what happens is your robot arm has a mass itself. It's also holding something or it's also pushing on something that has a mass. And so it's important to move all the forces to a reference point and then sum them up. So normally like the end effector is a good point to try to do that. All right, more questions.
Arlen,
What's up?
I have a question about the internal motion again.
That's fine.
So you're saying we don't need to find a specific say like a joint angles that basically makes the matrix ranked efficient. So what's our like answer going to be like in that case if we can't like suggest like
no, I said there, I mean, I can't say how the questions will be, but I just said that it's not going to be like tricky where you have to search through every possible angle from 0 to like 180 to find that. It's going to be some reasonable choice that you can think of.
Okay, got it.
Yeah. So
gotcha.